Hello everyone, this is a video for week 7 from my Algebra 2B class, going over finding probabilities. We're going to wait through a couple weeks of probability unit. Alright, for week 7, make sure you're going through all the sections in our textbook. Use this video and the textbook to take notes as you're working through paper pencil problems and any quizzes. Let me know if you have any questions as you go through all the topics for today. Our objectives for week 7. Here's what we're going to be learning. If I give you a binomial to some power, again, a binomial is a polynomial with two terms, can we use the pattern in Pascal's triangle to expand the binomial completely with the right coefficients? If I give you a binomial to some power, we're also going to use the binomial theorem and everything we've learned with combinations to expand the binomial. So we're going to combine our triangle pattern, everything we've learned with combinations and permutations with everything we've learned with polynomials. It's going to be awesome. Finally, if I give you a problem, we're going to do a little bit of probability. You can use the information to find the probability that an event will happen. We're going to find the probability of multiple events happening. And then if I give you a situation, we're going to create a probability distribution chart to show the probability of all the events happening. So lots of stuff. Hang with me in the beginning. It's going to get pretty technical and thick mathematically this week, but then we'll apply it into some fun, interesting probability problems. All right. What do you notice about the following pattern in this triangle? Start with 1, then we have a 1, 1, then we have a 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on and so forth. Do you see any patterns in what we call Pascal's triangle? Well, if you haven't seen it, the pattern is that we obviously go down with ones on the side. Always starts with ones at the beginning and end of each row. But then after that, we add the following. So to get this 2, that's 1 plus 1. We add those two ones together to make the 2. To get this 3, that's 1 plus 2 makes 3. And 2 plus 1 makes that 3. 1 plus 3 makes this 4 right here. 3 plus that 3 makes the 6, and the 4, and so forth. And you can keep going down each row by adding the two terms or two parts of each row together to get the what's beneath it. 4 plus 6 makes 10. 4 plus 1 makes 5. If I wanted to do the next row, it would be 1 and a 1. That's easy. It would be 6. 1 plus 5 is 6. Notice the next row is 1, 2, 3, 4, 5, 6. Kind of fun pattern there. 5 plus 10 makes 15. 10 plus 10 makes 20. 10 plus 5 makes 15. And 5 plus 1 makes 6. And we could keep going down further and further and further. Interesting pattern, right? And you can get all sorts of diagonal patterns. 1 plus 2 is 3. 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5, so it kind of adds by one more every time. You get all sorts of good patterns. What's interesting is that the patterns in Pascal's triangle can also be found using everything we know with combinations. Let me show you. Each row can be found by finding all the respective combinations. Let's start with this first one right here. That's just 1. That can be represented by taking all the combinations of 0 things, choosing 0 of them. So if you have 0 things, then how many ways can you choose 0 of that 0 things? Well, there's only one way, that's to choose none of them. The next row, however, can be found by taking one total thing, and then how many ways can you choose that one thing? Or taking one thing, how many ways can you choose none of those things? So we have 0 and 1. I actually should have written it as 0 and 1 that way. But there you go. Both of these, if you put them in your calculator, will equal 1. Let's move on to the next row. In this row, we're going to have the 0th row, the first row. Now we have 2 things. How many combinations of 2 things can I choose 0 of them? That'll be 1. How many combinations of 2 things can I choose 1 of them? That'll be 2. And then how many combinations of things if I choose all 2 of them? That'll be 3. Notice there's 1 for one term there, 2 different combinations for 2 things in this row. Here I have 3 different patterns for this third row right here. If I go all the way down to this row, I can represent each one of these terms as a combination problem. 0, 1, 2, 3, 4, 5. This would be all the combinations of 5 things. So n equals 5. So take a moment to calculate this. What if you have 5 things and we choose 0? 5 combinations of 0. If I calculate that, it's going to be 1. Then we have 5. All the combinations of choosing one thing out of 5. That's going to be 5. Then I have 5 and we choose all the combinations of 2 things. That's going to be 10. Choose 5 and all the combinations of 3 things out of that 5. That's also going to be 10. 5, choose all the combinations of 4 out of the 5. That's going to be 5. And finally, 5, 5. If I choose all 5, how many different ways can I choose all 5 out of the 5? That's just 1. We can do this for every single row. We can represent each term, each pattern here with a combinations thing. Pretty nice, right? So what if I was asked to find the 12th row of Pascal's triangle? Well, how would I do that? I could start writing out each row, and that might take me a long time going through the whole triangle thing. Or I could realize the 12th row means I'm finding all the combinations of 11 things. And so we would start the same way. If I have 11 things, what are all the combinations of choosing 0? Well, it's going to be 1. If I have 11 things, how many combinations of choosing 1? Well, it's just going to be 11. And I can go on so forth and so forth, 11 things, and find all the combinations of 2 of those things. And to do that, I'll have to get my Desmos calculator out, but that's how we would find out everything in the 12th row. Now, let's keep extending this with Pascal's triangle. Besides using combinations, I can also see a pattern emerge when I expand binomials to power. A binomial, again, has 2 terms. So there we got very generic, x plus y. There's my 2 terms. X and y can be anything. And we're going to take it to the first power, the second power, and the third power. Well, let me just do a little bit of math here and see what we get. If I take x plus y to the first power, that's only one of them. So that's just x. I'm going to write this down as 1x plus 1y. I should go back even further. Let me take x plus y. What happens if I take it to the 0th power? Well, everything to the 0th power just equals 1, right? So that's just going to be equal to 1. Now let's take x plus y squared. Well, that's going to equal x plus y times x plus y. If I multiply that, I get x times x to get x squared, plus x and y plus another x times y, so it ends up being plus 2 times xy plus y squared. And finally, if I multiply this is going to be like having 3 x plus y's times x plus y times another x plus y. And trust me, to keep this short, just trust me that it equals x to the third plus 3 times x squared times y plus 3 times x times y squared plus y cubed. Now, how does this all relate to Pascal's triangle, right? This is getting into polynomials and binomials and multiplying. Well, let me try and make this stand out a little bit here. We got a 1 for right here for the 0th power. To the first power, we ended up with a 1 and a 1. For second power, when we squared it, we ended up with a 1x squared plus 2xy plus 1y squared. And when I took it to the third power, we ended up with a 1 cubed plus 3 x squared y plus another 3 for coefficient plus a 1. This follows the direct patterns from 1, 1 and 1 right here, 1, 2, and 1 right there, and 1, 3, 3, 1 right here. These are just the coefficients when we multiply them all out. It's kind of handy, right? I like it. So all of these ideas, combining combinations, combining multiplying polynomials, combining all this stuff, Pascal's triangle, lead us to the binomial theorem. And all it is saying if I want to multiply any binomial out, it's going to follow this pattern. I can use combinations to find the coefficients of what should be in each term. All right, write this down. It looks crazy complicated, but it's really simple once you get the hang of it. You just need to be able to calculate all your combinations. Okay, so let's do this. We have 3x minus 5 to the 7th power. This would be quite large and complicated to just multiply all out using the distributive property. So instead, we're going to use the binomial theorem and make it a little bit easier. To use the binomial theorem, a couple things I got to start off with is I need to identify that a for this problem is a 3 times x. My b in this problem is going to be a negative 5. So anywhere where I have a or b, I'm going to put a 3x or negative 5 in place. Now n is to the 7th power. So n, with all my combinations, is going to be 7. All right, so let me do some things here. Get my calculator set up. Let's start expanding this binomial out. First of all, I'm just going to write it all out, but substitute some things, and then we'll go through and calculate it. So first of all is I have n, c, 0. So that's saying I've got 7 things. What are all the combinations of 0 of those 7 things? That's multiplied by a to the nth power. So I got to take a, which is 3x, and that's to the 7th power. But then I have b to the 0th power. Well, I'm not even worried about writing negative 5 to the 0th power because I can know that equals 1. So we already got the first term done. Okay, let's do the next term. Plus, now I have 7, nc1. So now I just have 7 things, but instead of choosing 0, I'm going to choose 1. I still got a, so now I've got 3x. But instead of to the 7th power, it's 1 less than that. It's only to the 6th power. And now I have 1 power of b. So I have to take negative 5 to the 1st power. You're going to see it's very systematic. Next term, I've got 7c2. 0, 1, 2. Can I see the pattern going on for our combinations? I have 3x, but instead of to the 7th power or 6th power, it's now only the 5th power. And from my negative 5, instead of 0, 1, it's now 2. So we just keep systematically going through, finding all the different possibilities. I have 7 things. Now I'm going to choose 3 of them. There's my coefficient. I still have 3x, but now instead of 7, 6, 5, now I'll have it to the 4th power and negative 5 to the 3rd power. Plus 7c4 times 3x to the 3rd times negative 5 to the 4th. It does get pretty long, even though it's just following the pattern all the way out. And then we got 7c to the 5th times 3x squared times negative 5 to the 5th plus 7c to the 6th times 3x to the 1st times negative 5 to the 6th. And our very last term, 7 things, all of the combination of those 7 things. 3x is to the 0th power, so I'm not even going to write that. I just have negative 5 to the 7th. There we go. 1, 2, 3, 4, 5, 6, 7, 8 different terms that we came up with following this pattern. And again, look at all your combinations. It kind of goes very systematic. We always have 7 things in all the combinations. But we start with 0, then 1, then 2, then 3, then 4, 5, 6, and 7. We just go all the way from 0 to 7. This gives us all that term of Pascal's triangle. It gives us all the coefficients, right? But then again, I'm taking A's and taking powers of A's. I'm taking powers of B's. And so how do we get all the powers of A's and B's? We start with A, and we do to the 7th power, then A to the 6th, then A to the 5th, A to the 4th, A to the 3rd. You see, it just goes down systematically. While A's are decreasing, our B term is increasing. B to the 0, B to the 1st, B to the 2nd, B to the 3rd, and we go all the way up to B to the 7th. Now, I'm not going to simplify all this math out, but let's simplify this term. So there's some things we can calculate, and if you can do this term, then you can go and do all the others as necessary. The first thing we need to do is calculate what is 7c squared. So again, using my combinations formula, that's going to be 7 factorial over 2 factorial divided by 7 minus 2 factorial. So the 7 and this turns into a 5 factorial. It leaves just 7 times 6 on the top because the 5 times 4 times 3 times 2 is divided out here at the bottom. But I was still also dividing that by 2 there. So 7 times 6 is 42, but 42 divided by 2 makes 21. So we have a coefficient of 21 right there. That's going to multiply 3x to the 5th. So 3 to the 5th power is 243. So it ends up being 243 times x to the 5th power. And then we have negative 5 squared, so times 25. So there's all the parts. There's the combinations. 7 choose 2 is 21 different combinations. 3x to the 5th is 243 times x to the 5th. There's that there. And negative 5 squared is 25. And I can simplify some of that down with 21 times 243 times 25. And let me change colors real quick. We get that this term has a coefficient of 127,575 times x to the 5th. And that would be, if I multiplied this out, this would be one of my terms in here. It's big because 7th power is big. Stuff multiplies a lot. I could do this for all the other terms, but again, to keep this thing short, I think you get the idea about how to multiply and simplify it out. But there we go. The third term in this polynomial, if I expand it all out, is 127,575 times x to the 5th. Whew. All right, so that's kind of the split. That's the first half. Is just we've worked on combinations last week. We looked at how to count things. We've done some polynomials. Now we just kind of combine those two things and to get into binomial probability. We're going to come back to binomial probability, that whole theorem. But now let's focus more on probability. What is probability? In case you need a refresher, probability is the event. The probability of an event happening. We need to know how many total different ways or outcomes could we have happen, and out of those, how many of those are possible desirable outcomes that we do want. That's kind of our probability formula. You have to count the number of outcomes and you have to count the number of desirable outcomes, and you divide them. Let's do an example with playing cards. A deck of playing cards has 52 cards in it. There's 4 suits, 4 suits, clubs, diamonds, hearts, and spades. Each suit has 13 red hearts, each suit, or there's 13 red diamonds, or 13 black spades, or 13 black clubs. Each suit, each of these 4 sets has the numbers 2 through 10. So 2, 3, 4, 5, 6, 7, 8, 9, 10, plus a jack, a queen, a king, and an ace. So here's our question. What is the probability of drawing a red? That means it could be a heart or a diamond. Those are my red suits. And an even numbered card. That could mean it'd be a 2, a 4, a 6, an 8, or a 10. What is the probability of drawing a red even numbered card? Okay. So the probability of this happening, probability of red and even. First of all, how many total cards are possible? All the total outcomes. Well, that's 52. There's 52 total cards. Out of those 52 cards, how many are red and even numbered? Well, there's a 2 of diamonds, 4 of diamonds, 6, 8, 10. So that's 5 in the diamonds, but then there's also 5 more in the hearts. So total, there's 10 of them, right? So there are 10 red cards that are an even number out of my 52. If I reduce that down, that reduces down into 5 out of 26. If I turn that into a decimal, 5 divided by 26 is going to be approximately 0.1923. That's my probability. But if I wanted to as a percent, that's about 19.23%. That's the chance that if I have a whole deck of cards and I draw one, it's going to be a red even number. It's a little bit about probability. We have to count the right amount of things and then express it in the right way. Now, if we have multiple events going on, so the probability of this and this and this and this happening, the probability of all those things combined is found by multiplying each event together. So here we go. What is the probability of rolling doubles with a pair of dice 3 times in a row? Again, if you play Monopoly, you have to be aware of this because you go directly to jail. If you roll doubles 3 times in a row on your turn, boom, you go to jail. So what is the probability of that happening? Well, let's think of what's the probability of rolling doubles. So the probability that we roll doubles we have to figure out when I roll a pair of dice, how many different outcomes can I have? Well, with 2 pairs of dice, one dice has 6 different outcomes. The numbers 1, 2, 3, 4, 5, 6. And if I roll another dice, there's 6 more outcomes. So the total of rolling a pair of dice is going to be 6 times 6, or 36. There's 36 different outcomes of rolling a dice. Now, how many of those outcomes are doubles? Well, let's think about it. I could roll a 1 and a 1. I could roll a 2 and a 2. I could roll a 3 and a 3 for both dice. A 4 and a 4. A 5 and a 5. Or a 6 and a 6. So that's 1, 2, 3, 4, 5, 6 different ways both those dice are the same, or doubles. So there's 6 ways to get doubles out of 36, which is 1/6 if I reduce it down. But wait a minute, we didn't want to know how often was it to get doubles. We want to know, what if you get doubles 3 times in a row? So let's think about this. The probability of doubles 3 times. Well, that's going to be 1/6. I roll doubles the first time. I roll doubles again, so that adds another 1/6 probability. I roll doubles again. There's another 1/6 probability. So the probability of all 3 of them happening is going to be 1/6 times 1/6 times 1/6. 6 times 6 times 6 is going to be 1 out of 216. Which if I divide those, That's a probability of about 0.00463 if I round it slightly, which is less than 1%, is 0.463%. So not a very high percent, right? Less than 1% chance you're going to roll 3 doubles in a row. But it seems to kind of happen in Monopoly. So it's not impossible, it happens. But here we go. According to mathematics, this is the probability that that will happen. Okay, back to cards a little bit. What is the probability that you're playing cards and you're dealt 4 aces in a row? So this one you kind of have to think about the situation a little bit. Again, we know we have 52 cards in a deck of cards. And we know in that deck of cards there are 4 aces. So what is the probability that I get 1 ace, the next card is an ace, the next card is an ace, and the next card is an ace? So the probability of 1 ace, the first card is an ace, is going to be, well, there's 4 aces out of 52 cards. So that's the probability that my first card is an ace. Well, what's the probability that the second card is an ace? All right, well, I've got 1 ace in my hand. There are only 51 cards left. And out of those 51, only 3 of them are aces. Now I've got 2 aces in my hand. What's the probability that the third one is an ace? Well, there's only 50 cards left, and out of those, 2 of them are aces. I think you get where this is going. To get that 4th ace in a row, there are 49 cards left to choose from, but only 1 of them is an ace. What's the probability that I get 4 aces in a row? 4 52nds times 3 51sts times 2 50ths times 1 out of 49. On the top, 12, 24, we got 24 divided by, let me multiply all those bottom numbers out, 52 times 51 times 50 times, let me try that again. 52 times 51 times 50 times 49, 24 out of 6,497, 400. Whew, it's not looking like a very good probability. 24 divided by 6497400. 0.0000369, which means we have a 0.0000369% chance. That is not very likely to happen right there. You have a less than 10th, 100th, 1000th, less than 1,000th% of getting 4 aces in a row. Really, really rare. These are kind of some fun problems, right? Now we get to up it. So we've got some understanding of probability. We've got our probability muscles working. Plus we've got all these binomial combination skills with Pascal's triangle and expanding things out. This lets us tackle some really interesting probability problems. Take a look at this example right here. On any given workday, there is a 15% chance that Professor Calculus will cause an explosion in his laboratory. We're going to use the binomial probability formula, that's what we kind of did way back in the beginning of class, to determine the probability that Professor Calculus will cause less than 3 explosions in a 5-day work week. All right, this one is definitely trickier to keep track of all that's going on, right? But let's kind of think through. Here is this formula that we can use to solve this problem out. N is the number of trials. How many times are we going to do this thing? Well, in this particular problem, we have a 5-day work week. There are 5 laboratory days, so N equals 5. Out of those 5 total days, we're keeping track of certain instances. All right, so now we got P. P is the probability that we have a success. In this case, we're trying to keep track of how many explosions, right? So in our probability problem, P is going to be 0.15 because that means that's the probability that an explosion happens. If there's a 15% chance of an explosion, we're going to mark explosion as a success. Not that we really want that, but that's going to be our P equals 0.15. R is the number of successes. R is going to keep track of, well, out of that 5-day work week, how many of those days are actually explosions? This problem is interesting because we want to know less than 3, which means, well, what's the probability that I could have 0 or 1 or 2? Well, those are all 3 options. So our R value, we need to calculate 0 explosions. We're going to need to calculate what if there's 1 explosion out of those 5 days. And we're going to need to calculate what if there's 2 explosions. Those are all the options or all the scenarios where there's less than 3. Okay, and then we got some combinations. This little thing here just means the same thing as total number n combinations of R. So if you see that notation, don't let that trip you up. That's just, we've learned that before with combinations. Okay, let's start figuring some of this stuff out. It's helpful to make a chart here with our formula and organize out all of our probabilities. So we're going to first figure out what's the probability that there's 0 explosions, then 1, then 2. We're going to calculate each one of these and then figure out the probabilities and then find out what's the probability that there's less than 3. Okay, using our formula here, the probability of 0 explosions is going to be found by taking 5, all the ways we can have 0 out of 5 days, times the probability of success. Well, there's a 15% chance of having an explosion, but we have 0 explosions, so R is 0. But we multiply that by the probability that there isn't an explosion, which is 0.85, and we have 0 explosions, which means we have 5 days without explosions, so we take 0.85 to the 5th power. There we go. If I calculate that out, I got the probability that there are 0 explosions. But now we still got to find out what's the probability of 1 explosion. Well, now we've got 5, choose 1. We've got 1 explosion out of the 5 days. The probability of an explosion is going to be 1 because we have 1 day with an explosion, but we have 4 days without an explosion. And we can keep going following the pattern down. I think you will really quickly see how it's kind of the same pattern over and over and over again. 2 days out of 5 with an explosion times 0.15, but now we have 2 explosions, so it's to the 2nd power. We have 3 days without explosions, so that's 0.85 to the 3rd power. And we could go forth and go forth. I'm not going to write the rest of these down because I think you get the hang of it, but we do need to calculate each one of these out. I'm going to go ahead and do this on our Desmos calculator so you can see exactly how to punch that in. All right, here I am at our Desmos calculator. We've got the keyboard pulled up. We're blank. We're ready to pull some stuff in here. Again, I got my formula. I know what I need to calculate. Let's pull up our combinations. I'm going to go to functions here. I'm going to go to stats. I'm going to pull up my combinations formula, NCR. For 0 explosions, we're going to choose 5 total days with 0 explosions. That's 5 combinations of 0 things. We're going to multiply that by our probability that there is no explosion to the 0th power times the probability 0.85 that there is no explosion. That's going to be to the 5th power. So we're just calculating that first one out real quick. And what do we get? We get 0.44. Rounded the nearest thousandth, I'm just going to call it 0.444. There you go. That's the probability that the whole week goes by and there are no explosions. Whew, that's kind of what we would want, right? We don't want explosions going off in the laboratory. But now let's calculate. I'm going to take the same formula, copy it there, but now we're going to change it a little bit. We're going to say instead of 0 explosions, what is the probability of having 1 explosion? So I got to put 1 there. We have 1 explosion, but 4 days without an explosion. And it's this probability, 0.39, we're going to round it to 2, round to the nearest thousand, so 0.392. I'm going to take that same formula, and now we'll calculate instead of 0 days or 1 day of an explosion, now we're going to calculate what if there's 2 explosions. So out of those 5 days, 2 of those days are explosions, 3 of those days are not explosions, and it's this right here, 0.138. Okay, I got those written down. That's how we calculate using our binomial probability theorem. All the different ways that thing could happen. Then we keep track of how many successes versus how many not successes when you just take the right powers. Notice these all 1 and 4, 0, 5, 2, and 3. They all have to add up to 5. There's 5 total things that we're keeping track of. All right, let's switch back to our chart here. So I don't have the formulas written down anymore, but we did before, and now we've got our probabilities. We know that the chances of having 0 explosions, that came out to be 0.444, which is about 44.4%. So pretty good probability that that's going to happen. We calculated 1 explosion. That came out to be 0.392. Again, we rounded all these to the nearest thousandth, which means that's 39.2%. And finally, we calculated out of those 5 days, 2 of those days were explosions. And that came out to be 0.138, which is about 13.8%. Notice the highest probability was having 0, but there's a pretty good chance of 1 explosion, but it went down a lot. There's not a very good chance of having 2 explosions. If we keep going down, you would see there's going to get less and less and less. If you totaled all these out, 0, 1, 2, 3, 4, 5, you would see that they should all add up to 100%, because there's a 100% chance that one of these scenarios is going to happen. Some of them are more likely than others. This whole column here, these should all add up to 1. Okay, but go back to our problem. Again, to answer this problem, what is the probability that there'll be less than 3 explosions? Well, that means I could have 0 or 1 or 2, and so I have to add all these together. So I'm going to do that really quick here. 0.444 plus 0.392 plus 0.138, and we got a 0.974 probability, which means it's a 97.4% chance that there will be less than 3 explosions in a 5-day work week. Which means it's going to be pretty rare that there isn't, or pretty rare that there's 4 or 5, which is good. That's how you do a binomial problem. You have to keep track of each scenario and figure out based on that what you need to know or not know. There's going to be a really similar problem like this on your weekly paper pencil problems. So this will be a good example for you guys to go through. All right, there you go. That's our week 7. We did a lot with binomials. We did a lot with Pascal's triangles and combinations. It used all this stuff to then be able to tackle some really good probability problems at the end and even get into some probability distribution. Let me know if you have any questions this week. Good luck with all your math problems.